All right, let's dive into one of the greatest detective stories in the history of science. We're going to look at how about a century ago, a few really strange clues completely blew up everything we thought we knew about reality. It forced us to create a whole new set of rules for a much, much weirder world.
So, to get us started, just think about this for a second. What if the universe isn't like a smooth, high-definition movie? What if, when you zoom in, and I mean way in, smaller than anything you can imagine, it's actually made of tiny individual pixels, like a digital image? That's the core idea we're going to explore, and trust me, it gets weird.
Okay, so let's set the scene. It's the late 1800s, and physicists, they were feeling pretty good about themselves. They thought they had basically figured it all out. Newton's laws covered everything that moved, and Maxwell's equations took care of light and magnetism. The universe seemed like this giant, predictable clock. But then, they found a clue that just didn't fit, a major one. They called it the ultraviolet catastrophe, and it was a doozy. Here's the problem. When scientists looked at the light coming from any hot object, their existing equations, the ones that worked perfectly for everything else, predicted something completely absurd. They said the object should be blasting out an infinite amount of ultraviolet energy. But of course, that's not what was happening at all. The real-world measurements showed something totally different. The old rules had officially hit a brick wall.
So, when your rulebook for the universe breaks down that badly, you need some new detectives on the case. And the first two were absolute giants, Max Planck and a young, up-and-coming physicist named Albert Einstein. And they didn't just suggest a small fix. They proposed something so radical, it would change physics forever.
The huge breakthrough came from Max Planck. He said, what if energy isn't a continuous thing, like a smooth ramp where you can stop at any point? What if, instead, it's like a staircase? You can stand on the first step, or you can jump to the second step, but you can never, ever hover in between the steps. Energy, he said, only comes in these distinct, separate chunks. And Planck gave a name to these little energy packets, quanta. A quantum is the absolute smallest piece of energy you can have, and the size of that piece is determined by this little formula right here, where h is now called Planck's constant. It's like a fundamental number that's baked into the very source code of our newly discovered pixelated universe. Okay, so just as people were starting to get their heads around that idea, another mystery popped up. It was called the photoelectric effect, and it was just bizarre. A really faint beam of blue light could zap a piece of metal and knock electrons right off of it. But if you took a super bright, incredibly intense red light and shined it on the same metal, nothing happened. Absolutely nothing. According to the old rules, where brightness meant more power, this made zero sense. And this is where Einstein had his big aha moment. He took Planck's idea and ran with it. He said, what if light itself is made of these quanta, these little energy bullets we now call photons? And just like that, the puzzle was solved. You see, a single blue photon has enough energy, enough of a punch to knock an electron free. A single red photon just doesn't. It doesn't matter if you send a billion of them. It's like throwing a billion ping pong balls at a brick wall. None of them has the individual power to do the job. So, think about what just happened. Einstein proved that something everyone knew was a wave, light, could also act like a particle. This was mind-bending stuff, and it led another physicist to ask a question that was somehow even more wild. If a wave can be a particle, could a particle be a wave? In 1924, a guy named Louis de Broglie put forward this incredibly bold idea. He basically said, hey, nature loves symmetry, right? So if waves can be particles, then particles, things like electrons, things with mass, they must also be waves. He was arguing that everything, absolutely everything in the universe has this strange dual identity. And here's the absolute kicker. De Broglie was right. It wasn't just a clever thought experiment. Scientists did the experiments, and they found that a beam of electrons would bend and create interference patterns, exactly like waves in water. Every single particle has a wavelength. Reality isn't just one thing or the other. It's somehow both, all at once. The next mystery on our list was, frankly, a potential universe ender. See, the best model of the atom at the time pictured it as a tiny solar system. But according to the old rules of physics, an orbiting electron should be constantly losing energy, causing it to spiral into the nucleus in a fraction of a second. Every atom in the universe should have collapsed almost instantly. So, why are we still here? The hero who saved the atom was Niels Bohr.
He took these new quantum ideas and applied them directly to the problem. He said, look, if an electron is also a wave, it can't just be anywhere. It has to exist in a stable, standing wave pattern around the nucleus. And that locks it into very specific energy levels, our staircase from before. An electron can be in one lane or another, but it can't just drift between them, so it can't spiral into the nucleus. The quantum nature of the electron is what makes all matter stable.
And we have perfect proof of this. When an electron jumps from a higher energy level to a lower one, it spits out a photon of light with a very specific color, a specific energy. These jumps are what give each element its own unique atomic fingerprint. Those colors you see in neon signs, that's direct evidence of electrons making these quantum leaps.
So we've figured out the electrons buzzing around the outside, but what about the heart of the atom, the nucleus? Well, turns out it holds an even crazier amount of power, and the key to understanding it is the most famous equation ever written. You know this one, E equals mc squared. What Einstein showed us here is that mass and energy are basically the same thing. They're interchangeable. Mass is just an incredibly concentrated, locked-up form of energy. And because c, the speed of light, is such a gigantic number, this equation tells us that even a tiny amount of mass is equivalent to a staggering amount of energy. And it all comes down to something called binding energy. It's the glue holding the nucleus together. Now, it turns out that nature has a favorite element, iron. It's the most stable, most tightly bound nucleus there is. So you can release energy by taking really heavy atoms like uranium and splitting them apart. That's fission. Or you can take really light atoms like hydrogen and slam them together. That's fusion. Both of those processes move you closer to that super stable state of iron, and they release enormous amounts of energy along the way.
Now, I know this all might sound like very abstract, cosmic stuff, but these weird quantum rules are the reason the device you're watching this on right now even exists. It's not an exaggeration. Modern life is built on this stuff.
See, in any solid material, quantum mechanics creates specific energy bands that electrons are allowed to be in. In a conductor, like metal, those bands overlap, so electrons can just flow freely. It's like an open highway. In an insulator, like glass or diamond, there's a huge gap between the bands, so the electrons are stuck in place. But the magic is in the middle, with semiconductors like silicon, which have a small, manageable gap. And here is the secret sauce of our entire digital world. We figured out that by adding tiny, precise impurities into a semiconductor, a process called doping, we can control that energy gap. We can basically tell the electrons when to flow and when to stop. This gives us the ability to build billions of microscopic switches, or transistors, which are the fundamental building blocks of every single computer chip on the planet. So think about it. We started with one broken equation about how hot objects glow, and from there we unraveled a pixelated reality, a wave-particle duality, saved the atom, unleashed nuclear power, and literally built the digital age. And all of that happened in roughly the last 100 years. It really makes you wonder, doesn't it? What fundamental rules are we getting wrong right now, and what incredible new world will we build when we finally figure them out?